So in this video we are going to look at our neighbors, or we are going to examine our neighbors. In this case it will be the neighbors of the starting node, but of course the algorithm will be written so that it actually automatically looks at the neighbors of the next current node all the time. There's a few things we'll have to take in consideration when we look at the neighbors. We'll have to make sure that they are walkable, and we'll have to make sure that the neighbor is not out of bounds, and we have to make sure that the neighbor is not already on the open or closed list, and we also have to make sure that the neighbor isn't our current node and it isn't the start node. So there's a few things we have to look out for when we write this code. So let's get to it. Open up your A* script. And when the script is open, we will have to add some more functionality to, let's see, to the A* script. I have a lot of scripts open here. Let me see if I can find the right one. Here we go. I'll have to add some functionality to this getPath function because we need to continue our search. First of all, we need to add 2 for loops to be able to look through all the nodes neighbors. Because if we do like this, and let's say this is our start, we will have to look at all the neighbors around here, all the neighbors around this one. So to do this, you can see we have a neutral position here. And if we need to go to the left, we need to say x minus 1, and we keep y as the same position because we're not going up and down. If we need to go down here, it's x minus 1 and y minus 1. If you want to go up here, it's x minus 1 and y plus 1. If you want to go up here, it is x equals 0 and y plus 1. Over here is x plus 1 and y should be 0. Up here, x plus 1, y plus 1. Down here, x plus 1, y minus 1. And down here, it will be x equals 0 and y minus 1 because we go down here. So we need to do something so that we can actually go through all these positions here. And to do that, we can just make a very simple if statement, or 2 for loops. Let's make one for loop that says -1, and it goes to +1 because we need to go to -1 and +1 in all spectrums. And let's call this one x and x like that. Yeah. So we make an integer called x. It starts on -1 and it runs until it is less or equal to 1. So we go -1, 0, and 1. Like this. Then we make another for loop and we call it y, and it runs from -1 to 1 again, like so. So now we have the for loop set up for actually going through all the positions here. As you can see, if I say debug.log here and say x plus, let's make a comma here, y plus, like so, then you'll see if we run this code now, just save it and we run it, you'll see that all the positions that we need will be written out. We click here and click space, then you'll see in the console -1, that's -1, that's the first position. -1, 0, well, -1, 0 is this one, -1, 1, -1, 1 is this one, and so on. So we have all the numbers we need to move around our current position now by creating those 2 for loops. So let's see, where was I? There is. So with that in place, we can actually save the position. So let's say point or position, yeah, equals new point. Okay, so we need to save the neighbor's position because we need to use the neighbor position to actually get the position out of, or get the actual neighbor out of the hash set or the list actually. So we can say current node dot grid position dot x minus x, right? So we calculate the x position of the actual node we need to look at. So the current node's x position, if that is 10, let's say the node is placed in 10.10, right? If say the current node is equal to 10.10, this being x and this one being y, right? Then the first grid position says x minus x, and x is -1 from the get-go. So the new position we need to check is 9, comma, and then the next one is -y. So we will say current node.grid position .y minus y, and that will be 9. So if our current node, our starting position is 10.10, then the first node we are examining is 9.9, one back and one down. So that's the diagonal node down here. Yeah, so that's what we are going to do. So now we have the position stored in a variable. So now we have the actual position of the node. We can also try to write that one up by saying debug.log neighbor position .x plus neighbor position .y, and then just make these in the between, and then save. Then you'll see if we clear this, we'll get the actual positions that we're checking. Click here, space, then you'll see 6.4, 6.3, 6.2, 5.4, and that's all the position around our starting node here we are checking. So now we have the positions. Okay, the next thing we have to do is to set up an if statement or so. But let's just, first of all, let's just grab our actual, let's grab the actual node that we need, because now we have a position. And actually we will need to create a node. So we can say node neighbor. Yeah, neighbor, and it needs to be equal to nodes. This is our dictionary. New point. Actually, you can just say a neighbor position. There we go. Can't we? There we go. So now we get an actual node out of this, right? And if we say this is only for debugging, the code I'm writing now, neighbor dot tileref dot sprite render dot color equals color black, just to test this out, right? So save this and jump in here and go here, and if we click here and press space, then you'll see it. Now I uncolored them, but then you'll see that it takes all the nodes around the actual starting point and makes them black. So now we have selected all the nodes we have around our start. But there's few things we need to take into account. For example, if we have a tower here and we click our start there and press space, then it shouldn't add this position, because this is an unwalkable tile and there's no reason to examine it. So we also have to do something about that. And other thing is also, if we put start at the edge here and we run it, then you'll see we get an exception, because it's actually trying to take some tiles that are placed right next to the start position, to the left of the start position, right? But the tiles doesn't exist because it's the edge of our map. So we also have to take that into account, so we don't try to add something that doesn't exist. Okay. Yeah. What else? I guess that's it for now. Let's try to add some functionality for this. So this code here needs to go into a actual if statement. We can easily find the position. That's totally fine. We can do that outside the if statement, because we need to use the position to figure out if it exists. So we can say if, and what should we do? First of all, we need to make sure that this isn't our self, right? So we need to say if neighbor position is not the same as our current node dot grid position, because this one finds everything within that square, which means that it can actually take itself and add it to the list and take itself as a neighbor, and we're not interested in that, right? So we need to make sure that that doesn't happen. So if our neighbor position isn't equal to our current node.grid position. Okay, so right now it is complaining. It says that the operator, the negative equals, cannot be applied to the operand of point and point. So we can't do like this to compare the points. But that's because we haven't implemented the functionality, because remember, neighbor position, not neighbor position, the point class is a class we created ourselves. So we have to add some functionality here to be able to tell C# or tell this project here how it needs to compare a point to another point. So to make this possible, we can say public static bool operator equals point x point y. So this operator is for comparing them like so. Let's see here. Is for comparing like this, but we need, now you can see it doesn't complain about this one, but we need this one as well, right? And the reason that I'm taking that equals is because this type of operator also needs the other one. So let's see here. So how do we compare this? We say return is x.x is equal to y.x, and x.y is equal to y.y. So this is our point, right? We can actually call these, let's call it first and call it second. Makes more sense. So we take 2 points, and this function here is called whenever we what's it called? Whenever we compare 2 points. So the first one is the first one to the left of the operators, and this one is to the right of the operators. It says, well, if the first x is equal to the second x and the first y is equal to the second y, well, then we can return that if that is true or false. Yeah, what else? And now you can see it complains here and says that, well, it needs the matching operator with the exclamation mark in front of it, right? And that's also why I'm making this one, because these can't be alone. So I can copy this one and make this one with exclamation mark, and then you see the error disappears, because you can't only implement one of these, you need to implement both of them for this to work. And then down here you need to handle it differently. You need to say if these are not identical or these are not identical, because if one of these are not the same, if x is different or y is different, well, then the 2 points are different, because 10.11 is not the same as 10.12, for example. The x's are equal, 10 and 10, but 11 and 12 is not the same in the y position, so it's 2 different points, right? That's why I use or here instead of and. Okay, with that in place, we can go back, and now you can see I can check if my neighbor position isn't the same as my current position. So that's one of them down. What else do I need to do? I need to make sure that the node is not walkable. So let's go to our where is it? Our tile script, and up here we can create a new bool. So let's say public bool. Let's just do like this actually. Property bool walkable like so. So let's see, we need to set this one to true or false, and by default all our tiles are walkable. So let's go to our setup and say walkable equals true. We don't have the need for setting them to walkable false from the get-go, I think, unless you for some reason have some predefined walls or something, then you might want to set walkable up here in the constructor when you create the tiles, but let's take that later if it's needed. So walkable is true from the get-go. Okay, when we place a tower, the walkable needs to be set to false. So let's see if we find our tile script. We have it here, and then we need to figure out where we're placing it. We're placing a tower here, and then we need to say, let's say when we're done buying the tower, then let's say walkable equals false. There we go. Okay. Then we also needed to go to our A star and then we need to say if our actually neighbor node, let's do like this actually here, and then we can say, well, we need to check if it is walkable. And yeah, the easiest way to do that is to go to our level manager and instance and tiles, and then take our neighbor position and say walkable. So if this tile here, if it's walkable, well, then we can easily ignore it. We can easily add it to our search. But if it's not walkable, well, then we can just move on. Okay, so let's try to save this. Let's see here, neighbor tile with. Yeah, okay, that makes sense. Just uncomment this one. We don't need this one to paint it black anymore. Actually, I can just delete it. It was just for testing and debugging before. Or nope, let's leave it and then put it in here in the if statement now, because we would like to test if this works, of course. There we go. Okay, so let's save this and jump back to Unity and clear this error. Run the game. Place a tower. Place. Sorry. We need to place start right next to it, so let's do like this, and then press space, and then you'll see now it didn't add the tile with the tower on it because it's not walkable when we place the towers. So now we are sure that we're never trying to go through any towers right now. So we just fixed that right there, so we'll never put a tower in the path, in the way of the path. The next thing we'll have to fix is the fact that it still bugs over here. When we press space, we still get this exception here. So we need to make a check for that. And we can actually make a check for that in the level manager. So jump to the level manager and go to the top. And in here we can create a new field. Let's see, let's make a private point somewhere. Just do it, yeah, I don't know. Just do it anywhere. Private, actually, let's keep the map stuff together. Yeah, here. Private. Point private. There we go. Point map size. So we need to set the map size somehow. And the map size can be set inside the create level function. And we can do it right here. And we can say map size equals new point. Map data 0 to char array dot length. So now we get the length of the x by saying map data 0, because it's the first part of the map, the first row of the map. Then we can say map data dot what was it, length, just to get the y. Yeah, there we go. So this is the x value and this is the y value, because the first position here on the map has an exact amount of values based on the x-axis of the map, and the actual length of the map data is the y value. So we can get the map size like this. So now we have the map size. Then we can create a new function, and this function will actually it will test if a tile is in bounds. So public bool. So it will return a bool based on the condition in here, and we call it in bounds. And we can call this one point position, and then returns return position that x is larger or equal to 0, and position that y is larger or equal to 0. So because we don't want to go, we can't have a position in our grid that is minus. The first tile is always called minus 0. Not minus, sorry, 0.0, and that's this one, right? So if the tile position is larger than 0 or equal to 0, then it's totally okay. But if it's negative, well, then it's not okay, because then we are outside the bounds. So this one will fix the bounds on the left side. We can do like this actually, just to test this. Save and go to A star. and then go here and say level manager dot instance dot inbounds, and then in the position, neighbor position. So this one checks if the neighbor, and then write and after. This checks if the neighbor up here is in bounds, right? And this, we can do this because our level manager function here returns a bool, so it returns true or false based on if the neighbor has a position that is negative x or negative y. And if it has a negative value, it returns false, so we can't check that neighbor. And if it has a positive value, then it's fine, then we can check the neighbor. But it wants me to log into Unity. Let's try here. Clear, run here, click here, press space, and you'll see no exception, right? No exception, everything's fine, but we are not checking on the other end of the scale, right? So if I place it here and press, then I get an exception because these tiles over here that would lay here doesn't exist. So I need to check for this side as well. So I can go back here, and in here I can say and position.x is less than map size.x, and position.y is less than map size.y. There we go. So now our inbounds function works for both end of the map, and we can try to run this again. Move all the way to the right, place it here, and press space, and then you'll see we didn't get an exception. We didn't try to check out here, but we got the neighbors right next to our start position. So now we know our neighbor checking actually works. So we can just go back to A star, and we can remove this line of code neighbor tile with sprite renderer because we're not going to need it. Okay. So now we can check our neighbors, we can register our neighbors, and that is basically what we would do in this video. And the next video we will start maybe scoring the neighbors, adding them to the open list and so on, but we will take the next step in the A star algorithm. So thank you very much for watching, and remember to follow me on Twitter, like my Facebook page, and subscribe to the channel. Also remember that Inscope Studios is a community founded site, so all your support really helps me out a lot. You can support me by getting this project or any of my other projects by clicking the link in the bottom of the screen, or you can support me on Patreon, and if you do so, then you can get every single project and all the sprites and assets that I've created for all my tutorials here on YouTube. So thank you for watching.